Good afternoon, everyone. Thank you so much for attending our webinar today. My name is Desmond Martin. I am the Chief Learning Officer at NextWaveSTEM, and it is our very good pleasure to have you with us. Um, I have the distinct pleasure and opportunity to talk with you all today about remote learning robotics, increasing STEM engagement for diverse learners. Very exciting because what we've learned in the past year is that STEM with students in some really unique, really difficult, and really unprecedented circumstances can be extremely hard. There are really some great opportunities that have been afforded to educators through simulation. There have even been some really amazing opportunities for STEM education when we think about actually being able to afford students hands-on kits, those opportunities to really get hands-on. And you work with robotics wherever they may be working, whether in a hybrid scenario or a remote learning scenario. What we've also learned is that we have particular student populations that can also be really well served with robotics. Um, and that's what we want to talk about today, what those student pathways are, what those pipelines look like, and how we can make those learning opportunities readily available for our students. So I'm really excited to jump into that with you all. Before we push forward, I do want to do a little bit of logistics work, just setting some of the house rules and ground rules for today's webinar. We are in webinar mode. That means that even though we know you're camera ready, everyone out there has become a Zoom expert. You know exactly what you're doing and exactly how to engage with us in some really amazing ways. We won't be able to hear your voice or see your face. However, you're not completely voiceless out there. If you have any questions at any time, feel free to jump in to the chat and share those questions with us. There is no such thing as a bad question, and we can get those questions answered live on the air today. The second bit of information is just to let you know that if you need to step away at some point during today's webinar, no big deal at all. We are recording and we will be sharing a recording of today's webinar with you. So you can share this with your colleagues or just use it as an enduring resource for yourself as well. Really excited to have our guests on. I see a couple of faces, or names I should say, because I don't see any faces. Hey there, Kathy. Great to have you with us as well. Hey, Liz. Thanks so much for joining. With that being said, we'll push forward and do a little bit more of a formalized introduction for those of you who may be joining us for our webinar for the first time today. At Next Wave STEM, we really, truly, deeply at our core believe that our future problems and some of the most pressing issues, most dire needs that humanity and society needs met are going to be met by this next generation of young learners. And that they're going to be meeting those needs and solving those problems using advanced and emerging technologies. Things like 3D printing, robotics, drones, artificial intelligence. Those technologies are going to be key to literally saving the world. But we also understand that these young learners need educators, need access to resources, need the experience and those opportunities to learn about those early technologies from a young age. We understand that importance because students, on top of learning about these technologies, also need to build identities in STEM. Um, the analogy that I like to make is actually myself, as a young learner, I actually play the violin. I haven't touched it in years, so if I tried today, it would probably not be a very pleasant experience. But for the first couple of years of learning the violin, I was mediocre, not for lack of practice time or lack of instruction, but because I was afraid. I had this beautiful instrument and I was afraid to really explore and push my own personal boundaries just because I didn't want to break this thing. We want to give our students the opportunity to really dive in, to get hands on, to not be afraid of breaking things, to even show them that sometimes our mistakes, oftentimes our mistakes actually, are amazing opportunities for learning and for growth. And in order to do that at NextWaveSTEM, we work with teachers like you to empower our students. At NextWaveSTEM, I mentioned before, we are focusing really on emerging technology areas. And that means providing curricula, actual licensed courses that you can work with your students in the classroom in robotics and AI, drones and 3D printing. And all of our curricula are designed for your needs. They're 21st century skills aligned, NGSS, as well as Common Core Math and ELA standards aligned. What's important for us is that you as a teacher, if you yourself are not familiar with emerging technologies, if you need help really growing into being a more proficient STEM educator, NextWaveSTEM is here for you. So I mentioned a little bit earlier before that, hi, once again, I'm Desmond. I'm the Chief Learning Officer here at NextWaveSTEM. And before working with NextWaveSTEM, my professional experiences both in education and ed tech supplementation. I spent a couple of years in the classroom as well, teaching at the high school level, and I had a small tutoring business that I was running in Detroit. But my pedagogy, my professional growth is in mechanical engineering. For those of us who are here, we would love to learn more about you. Some of us have already said hello. Hey, Eric, nice to have you with us. If you want to share where you're from and what you teach in the chat, that would be awesome as well. So kind of what we mentioned at the top, we want to explore ways that robots cover multiple subject matter disciplines and how we can use them for different learning modalities. A great place to begin, and this may seem a little bit strange, is just this basic idea of what a robot actually is. And the reason why we want to start here is that when we think about emerging technologies, that has kind of a very amorphous sliding scale idea for what we mean by emerging, what we think about as being the next wave of future technologies that students will use to solve problems, that will be um, their actual fields in which they will earn their livings, will make huge impacts in the world. And for all of the technologies that NextWaveSTEM works with, robotics is the oldest, and it's also the one that honestly has touched the most different areas of our everyday life, thanks to its age and distribution. It's useful then to think about the definition of what a robot is and what it does, because we have to first and foremost address our students' perceptions and address our own perceptions as educators. So we'll take it right down to the very beginning. What is a robot? I had a speech professor back at the University of Michigan, go blue, that told me, taught us as students that you already can tell that a presentation is going to be bad if they start with a definition. We're a little bit of the way into our webinar today, so hopefully we're not going to be very, very bad, but we're going to hit you with a couple of definitions as well. And yes, we will be sharing this presentation after the webinar as well. You should get an email with that follow-up probably tomorrow morning. A robot is a machine capable of carrying out a complex series of actions automatically. That's especially one that's programmable by a computer. Seems pretty simple, but it's very, very interesting because this idea of a machine, some kind of mechanical collection of parts working together to do complex actions, has actually been around for thousands and thousands of years. And it differs a little bit when we think about modern robotics, because this machine that carries out complex actions is programmed by a computer in almost every situation. But our really standard definition of a robot does not say that the machine has to be programmable. We have established for us this idea that a robot is something that's going to be doing some physical work. And all of this seems really amorphous, but it's important for us to keep locked in to that understanding because we end up branching out much, much further the more we think about robotics applications. So where we begin is thinking about what robotics covers. If focusing on what a robot is individually is a little bit too amorphous, then it becomes really useful for us to deal with the branch of study. Robotics is the branch of technology that deals with the design, construction, operation, and application of robots. I love this definition because it tells us almost everything that we need to know about studying robotics and that it's an integrative field. When we think about working with robotics, when we think about teaching robotics, when we think about teaching our students robotics, when we think about assessment with robotics, when we think about school to career pipelines in robotics, it is critical, it is paramount for us to understand that we're just not talking about a specific machine. We're talking about the engineering design process. We're talking about physical, career, and technical education skills with construction. We're talking about computer science. We're talking about machine human interface. We're talking about actual process design and solutions design around the use of these specific machines as well. So already, instead of focusing on the machine, we need to be thinking about the entire ecosystem in which a particular machine or machines might get used in. This paradigm shift is really important because we'll use it to make the learning real for our students. So if we're thinking about what a robot is, backtracking just a little bit, we know that this robot is going to be doing some automatic operations. It's going to be moving by itself. And when it's moving by itself, it's going to be doing some kind of work. Now, taking us back to our high school mathematics class or high school science class, we're not talking about just work in terms of the tasks that we might be given throughout the course of the day. Robots might help with that. But what we're physically focused on is scientific work, an application of force to move an object from point A to point B. We're talking about moving through the physical world. And this becomes critical. It becomes critical because it allows us to make a separation, a differentiation, not a separation, but a differentiation between robotics and artificial intelligence. Very thin line, but really important distinction to make there. When we think about robotics, they're used extensively in construction, logistics, and manufacturing. I am a Detroit native. That means that I've been raised and steeped in a culture that one embraced robotics really, really early. Detroit is one of the United States' earliest and oldest tech hubs when you think about industries and companies that have clustered together in a region in order to produce and advocate for the application of technology. Silicon Valley is another one of those spaces. But we also need to understand that the application, the physical application of technologies, and in robots in this case, will literally change the face of our physical environment. The automobile during the course of the 40s, 50s, and 60s literally changed the landscape. Thousands of miles of federal highways being constructed, tens of thousands of miles of roadways being constructed in cities. The ways that our cities are designed is different because of this application of technology in the car. The way that our houses are designed, the way that we were structured for work, all of those things are completely different now because of the application of technologies to change our physical environments. And the car, the modern car that we know it, that process for building a car is a combination of human and robotic work that was pioneered in the Motor City in Detroit. I'm very, very proud of my place of birth. This application of technology to change our physical world and the way that we move through it is at the heart of what robotics is about. If we can get that locked into our understanding for the importance for robotics, and we can communicate that to our students, then we are on the right path just to begin with. Now, one really nice and important distinction to make here is between robotics and artificial intelligence. Very thin line once again, and they work together in concert. But it's useful to draw this thin line because when we're working with robotics, we don't want to put the cart in front of the horse when we think about artificial intelligence. When you talk about robotics, you're talking about physical work, moving something, displacing an object, applying force. When I speak to the smart assistant on my phone, I'm not going to say any names because I don't want to set anybody's devices off. Those assistants are not robots. They may be called bots colloquially, but they're not robots because they don't do any physical work. As opposed to something like we see on the left-hand side of our screen here, the Atlas robot, which physically moves objects, in this case, picking up boxes in a warehouse. Um, the application of work is critical. When we're working with our students, yes, they will learn computer science. It will be critical, but what they will not really be doing with robotics is feeding in that large amount of data, usually some kind of environmental statistical data, in order to just give us back a display amount or some kind of return value. We want something to physically move and change in our environment. This becomes critical. And this becomes really empowering for our students who are looking for ways to make physical changes to their environments and the ways in which they interact in them. So we've talked about a little bit about what robots are, but it's useful now to think about the ways that robots are being used in industry right now. We're kind of setting up this idea that, okay, we've been using robots in industry for decades now, manufacturing all kinds of things. What's going on with robotics today? What's changed? Well, the first thing that's useful to know is really this context for the way in which we interact from an industry perspective with our constructed world. It's called the Fourth Industrial Revolution. Back in 1784, we actually have a specific year here. Um, Mechanization with steam power and hydraulics allowed us to make big machines that could move and change the environment. It was physical breaking labor, completely unethical, many lives lost to lay railway across not just this country, but many countries. But we saw the ability now to transport goods and people and ideas all over the world. For those of us who are familiar with the Sprint company, telecom that's now part of T-Mobile, they began their life as a part of the railroad industry. This idea now of being able to exchange goods and ideas over a long period of time through mechanization, through steam power, is huge. And then we took these ideas. Mechanical engineering basically gets its birth, it gets its modern birth during this time. And we're able, with a combination of electricity, to start mass producing items and objects. That's Industrial Revolution 2.0. That's also where we think about this massive amount of coal and petrochemicals being used as well. That's kind of the generation of our global warming issues. But we move into 3.0 with computer science. Computer science, mechanization, and integrated technology allows us to make and move more things, people, and information than we ever were able to before. We're designing our systems in computers instead of on paper. Eventually, we're sending emails. We're actually exchanging information by satellite all over the world. The globalization of our world really begins at this point. And what's different today are this idea of the integration of cyber and physical systems that hardwired into our built environment are also the tools that allow us to interact and change that environment. How do we know this is true? Our actual teaching pedagogy and practice of the last year is a direct reflection of that. 99.9% of educators have had to engage in teaching that one, 12 years prior would have been logistically impossible. The bandwidth didn't exist, the technology didn't exist, not en masse. Um, the infrastructure in terms of the internet going into family homes might not have even existed to a level that will allow for remote learning for our students en masse throughout the country, actually throughout the world. Um, but two, the idea that we can interact with these systems in our democracies and in our manufacturing processes. These infrastructures are all tied together. And we see that reflected in the products, goods, and services that we use every day. Um, Once upon a time, when computers were coded in a program called COBOL, that many of us have never really seen before and might not have even heard of before, computers took up entire buildings. Now I've got a computer that is exponentially more powerful than that first computer that can fit in my pocket and that costs virtually pennies to produce as compared to those first machines. The way that we think about our infrastructure and how that will change once again for the way we move goods and services will change because of automation. Things like self-driving cars, self-driving trains, self-driving aircraft. Those autonomous vehicles will eventually, not immediately, but will eventually supplant the ways in which people move around today. And then even those traditionally handcrafted, really time intensive industries like garment making are still being automated and industrialized in faster and faster ways through robotics. Entire factories where we saw rows and rows of workers are being placed instead by rows of machines working much harder and with much more efficiency. And of course, we have to consider the trade-offs of these things. The waste and the power used to generate more stuff and move more people, but also thinking more smartly about how we use what we are building and what we are making, um, and we and being much more smarter about the ways in which we're changing our physical space or changing our physical environment will have impact for future generations as well. They go part and parcel. So now that we have this really big, high level understanding of the robotics industry, it becomes critical for us to think about the pathway for students. How do they engage? How do we transform them from just being consumers of this technology, being those who are just buying things or using services, to actually being creators of the technology, who are learning the platforms, who are learning the principles and skills to go forward with their education, and then start to make products in different processes with less environmental impacts, with really lasting impacts for themselves and for their employment in the future. How do we get students started? Well, the first thing we have to consider is understanding our expectations. We have to set expectations for not just what we would call an average student, because we understand that an average student doesn't exist, that student populations are diverse in a couple of different ways, and that we can make the technology available for those diverse populations to serve our educational purposes and our students' educational goals. We can think about them as domains and ranges that are really simple for us to really break down and and consider robotics applications. So if you're thinking domains, this is really high level and rough, but we can think about it in the elementary space, in the high school space, and then in the special education space. And in each one of those domains, we have ranges that apply that will allow us to make some good decisions about robotics education. The first being previous and prerequisite experience. We can think about this as the cross-disciplinary learning that students will have to engage in effectively in robotics. And we're not just thinking about their hard skills, but we're also thinking about social, emotional learning skills, collaboration, creativity. We're thinking about their abilities to be resilient as well as their hard skills in math in working with physical manipulatives in construction, and being able to understand robotics applications even through social studies or statistics. Those previous and prerequisite skills become important to consider, and that ties in line with the idea of age appropriateness and experience for our students as they've been matriculating. The second thing that we should consider also is equipment access and availability. And here's where I want to put a really big pin in this thing. Um, we have seen tremendous, tremendous opportunities when we think about students' abilities to simulate. At NextWaveSTEM, we understand that student populations that just don't have the resources to get hands-on one-to-one or even in teams with robotics platforms, for them, simulation is a golden opportunity. It's the chance to, one, engage in the computer science, but then two, have some taste of the way that their physical robot would actually interact with a virtualized world. That becomes important because we're getting that input output, the direct feedback of our performance tasks, and even thinking about how we can still assess based on what our students are trying to accomplish with their challenge with the robots, with the intended application. But the third thing that's important is this idea of integrated learning pedagogy. Our students, once again, are not just learning one thing when they work on a robot, when they work through a robotics course or through a robotics program or compete. They're learning in pulling together multiple disciplines at the same time. And depending on whether or not your students are in elementary or high school or in special education track, it's important to think about how our actual pedagogies around their content area or their content disciplines actually work together as they are building the robot. Considering the ways that we expect our students to engage, even speaking taxonomically, if you think about Bloom's, our introduction and the way that we introduce the purpose of a robotics platform in physical space for an elementary student is going to look very, very different than it would for a high school student. And the way that they bring those understandings together in their robotics learning and building and usage is really going to reflect that. One thing that's super important to understand about this is that because we're integrating different practices together, we're setting up a scenario where you as an educator should not be thinking about ways to micromanage your students here. Um, and I will let you all in on a really important secret when we think about robotics education. Um, when we're thinking about robotics education, we are really, really closely aligned to engineering. That E, when we think about STEM. Science is exactly that, this understanding of the natural world around us. Technology is the application of what we learn about the natural world to create tools that we can use. Mathematics is really closely related to science because that allows us to quantify that world, understand it through numbers, and in a lot of ways as a science unto itself. It's the way that we can describe in a universal language what's happening, a way to describe reality. Engineering is special. Engineering is special because it is the only discipline in that acronym that is explicitly human focused. Engineers take science, technology, and mathematics and use those things to solve problems. And the right now, when we think about problems, those problems are from a human-centric perspective. Um, we want to save our world. We want to actually make sure that we don't destroy the planet because that causes a huge problem, not just for all of the things that are living on the planet. There have been mass extinctions before, and we still have life on the planet. But those huge problems are for human beings. We would like to continue the work of metacognition that we are doing when we are living here on the earth. Um, and in that way, focusing on human problems, we have to give our students the range to be able to work in multiple facets of problem solving. They have to be able to understand that there's more than one prescribed way to solve a problem. Limiting their opportunities to do that is countermanding the whole idea of learning about engineering and really takes the teeth out of our study with robotics. When we think about those social and emotional skills, once again, we're pulling in multiple disciplines and we're even thinking about not only the problem solving ability, those abilities to apply technology and mathematics, but we're also thinking about ways in which we are encouraging growth in motor skills as well, fine motor skills, but also this resiliency, the ability to function, to fail, and then come back and function again. This is a super critical point here. We're not just doing coding, we're not just tackling the challenge, we're not just building the robot, we're doing all three things at the same time. When we're setting up this idea for understanding for our students and this way to get students engaged, it's also important, especially at the high school level, to think about the actual technology and pathways that will lead to industries, both in robotics and robotics adjacent. So the big question here is, how do we perceive those growth opportunities? How do we set our students up in such a way that they can take advantage of those things? Well, the first is understanding that even though we might not be on the front lines of robotics industries ourselves, we know that our students will. And for some of us, we've seen this in real life, real world application right from our own front doors. This is a little bit of older data because it's already 2021. But back in 2019, there were 2 robots for every 1,000 human workers in the workforce. And we know that that number will have doubled by the time we reach 2025. Jobs that were done exclusively by workers working by hand, like welding, are more increasingly being done by robots. And we see that trend increasing in multiple industries and factors and fields. So we want to make sure that we're giving our students those opportunities to really engage. So saw a really good question there. What kinds of assessment will we want to work towards when using robotics? This is kind of where the rubber meets the road for a lot of us. And what should our assessment, what should our take on assessment be for emerging technologies generally? This is a really, really sticky, controversial subject matter because many of us might agree with this or might disagree. But our traditional mindset around assessment, especially with emerging technologies, is much, much, much different than what we actually see in terms of assessment and application for learned content, but also just problem solving in the real world actually looks like. Two different kind of modalities that our students have to engage in. Assessment for robotics and really for emerging technologies in general, but especially for robotics, gives us the ability to assess via competition. When we think about the purpose of assessment, assessment is there to do a few different things for us. It's there to allow us to understand whether or not our students can demonstrate the skills that they've learned in their time with us in the classroom, and also that they're able to demonstrate problem solving abilities as well based on those skills. Do you have the skills and can you apply them to solve a particular problem? And the thing is, oftentimes what these assessments don't capture is our abilities to work with other people as we apply these skills. There's one thing to be said if I've got the individual skill set to solve a particular problem, even if it's a very, very challenging problem. It's a completely different thing to be able to do work more efficiently and solve those problems in the context of a team environment. And that's the world we live in today. This is about communication. It's about collaboration. It's understanding that there's literally no one person who exists in the world that can solve these massive and complex problems by themselves. Um, I'll go back to this example of the iPhone. The iPhone, the modern smartphone of any kind, is a culmination of thousands of years of scientific inquiry, work in fields like metallurgy, computer science, semi-processors and conductors, photography, holography, the whole gamut of different STEM industries, and tens of thousands of years of man work in developing and design. There is no singular human being who can go out into the environment and go from raw metallic material or earth and then fashion a completed iPhone. It cannot be done. The massive problems that we have require teamwork. So this ability to assess both our individual understanding of the challenges and our ability to apply the solutions and the ability to assess um, our team-based final product, which is especially important when we think about actually creating a product that solves a physical human problem, cannot be overstated. Our standardized tests do not do that. They don't even do a great job of really oftentimes assessing students' understanding and applications of the subject matter that they've been studying with us for 10 weeks or 20 weeks. Um, what we need is the opportunity to assess our students both individually and, and collaboratively in the best way that we've seen that done is through competition. The analogy that I can make here is for those of us who have participated in sports, who might love sports, who have family members that love sports. If you've ever played a team sport, you understand that you can control what you can control, and then you also have to rely on your team and be a team member. Those greatest champions are doing both. They're both great individuals on those teams with a robust understanding of their skills, strategies, and tactics to solve individual problems, but also fit in tremendously well with their teammates, coaches, and staff. The success and challenges and team competitions, along with the individualized work output of our students at those actual individual levels. And there may be good place there for formative and summative assessment at the individual level. But we want to add on this important layer of working together in teams to demonstrate skill mastery. So what are our next steps for students? We have this idea of pipeline and even how we can assess, how we can get them started and what we should have our students consider. Well, we want this idea of robotics, a STEM curricula. If we had unlimited resources If we could design an ideal course for our students with no restrictions on budget or materials, what would that course look like and why? And I have a really favorite answer to this question. We should think about project-based learning. And the reason why we should think about project-based learning is that it gives us the opportunity to, one, really empower our students, give them the ability to make choices about not just what they are going to learn and study, but also the actual performance tasks that they'll use to get there, how they'll collaborate, how they'll work individually, how they'll communicate what they learn. But it also focuses on our students' abilities to be investigative. It gives them the chance to master asking questions and learning how to go and get those answers if they don't have them themselves. This becomes critical to the way that scientists, technologists, engineers, and mathematicians work in the field. Um, they're learning not just how to solve problems, but to get answers as well, and to do that with teams of people. And they're self-guided in this work. So creating a structure, even a decision tree, if you will, for our students to follow and for them to branch and explore, gives our students the opportunity to really come up with some unique solutions, but also gives us plenty of opportunity to help reflect with our students and give them feedback and assess them in both formative and summative ways at each step. So when we think about project-based learning, really at the beginning with robotics, it's creating this context in which problems will be solved. And it has to be a real context, something that exists in as a problem for people at the local, national, state, or even international level. What's the problem that's already there that you experience every day? That could be as simple as I'm driving to work and I see too many car accidents. Do we need to physically change the road? Can we do that efficiently and with low cost to the taxpayer? Or do we have to consider who needs to pay for that? Or if that's too expensive, can we change the vehicles that drive on the road? Should those vehicles drive themselves? Should there be some other automated systems in place that would reduce fatalities? Who pays for those things? You have to consider legislative tools at play, manufacturing tools at play, um, industry pipelines and chains of materials. Even right now, there is a microprocessor shortage. There's a chip shortage that's actually stalled out auto manufacturing in multiple countries, including here in the United States. What do we do about that? It's important for us to ensure that we're solving real problems for real people and that the solutions that our students are generating are actually viable real solutions, even if our students may never have the physical resources, either the financial or political capital to see those solutions come to fruition. The beautiful thing there is that sometimes our students do have those resources, or we can make those resources available. And we see our students' project-based learning become actual real-world solutions. Those things that we want, our students changing the world for the better. And it's important when our students are working through PBL that we're building this experience with a goal in mind. The assessment and the learning should be worth it. If we're building a robot, if we're taking the time to go cross-disciplinary and think about the importance of technology and changing our physical world, this experience should be fun. This should be something that, just like BattleBots, causes our students to say, wow, yes, I want to continue to participate because it's fun, it's entertaining, it's going to change the way I perceive the field, and it's going to change the way that we interact. So I hate you with kind of a fire hose of information, but it's good information. The next thing I want to leave you with is what we do at NextWaveSTEM and how we can actually be effective in helping. I mentioned before, we've got courses, licensed courses that you can purchase for your school district, for your educators, K through 12, in our robotics and AI track, in our drones and coding track, and in our 3D printing track. Um, we're here to cover entire spectra, an entire strata, I should say, of student needs when we think about emerging technologies. It's important to build taxonomically on our students' experiences so that they build STEM identity in some really robust ways. Um, So we're just doing this through standard progression of knowledge, building layers upon layers of understanding for our students as they solve increasingly challenging problems, but are also doing increasingly cognitively demanding work. For our K through 2 learners, this is their first exposure to these particular technologies. Oftentimes, and that means that we're setting expectations, but we're also building in the understanding of the technologies that we use as being useful in the real world. Our students in the grade 3 through 5 build upon that understanding. And for them, it's about seeing these tools and technologies not just as fun, but as things that are actual career paths, things that we use to help people. In our 6th through 8th, getting into middle school, students are going to be more analytical. They're going to be really starting to evaluate the effectiveness of these technologies as solutions, a way to bend these technologies to their will so they become more effective solutions. And in the 9 through 12 courses, our students are really laser focused on building solutions to these problems. That becomes super important, that they are actually able to work through these problems and try to demonstrate solutions that can make a difference in the real world. When you work with NextWaveSTEM, what you're getting is equipment, the license for the actual curricula, and all the actual lesson material, teacher's guide, presentations, answer keys, but also continuous professional development and training support. When you work with us, you'll get a half a day of instruction on how to use this emerging technology. If you're emerging technology newbie, if you've never worked with a drone or with a robot or with a 3D printer, we teach you how. All of our courses and our materials available through our LMS with additional access that's available. And we can even get customized and add on support. You may need professional customized professional development on technology that we might not work with in NextWaveSTEM, or you may need additional equipment for your students in class. Those are things that we're able to get you help with at NextWaveSTEM so that you're teaching STEM with fidelity and confidence. So I want to pause at this point, and leave the floor open for any questions that you may have. Are there any questions that you may have about robotics or about integrating different practices for different student populations? The comment section is open for any of your questions, and so is the Q&A section. And remember, no question is a bad question. Scrolling through our comments here. Yeah, Kath, we did touch on assessments a little bit earlier. I'm hoping that was a bit helpful for you. Well, we don't have any questions coming in, but if you're chewing on those questions, that's definitely something that you can reach out and contact us about more. Just got a question here. How do we motivate inner city youth? That's a great question. When we're thinking about robotics and emerging technology, generally, what's really important is giving them the opportunity to see the connection between the work that they do in the classroom and what affects them in their everyday lives. The example that I use, especially with robotics, is the fact that 95% of everything that our students use is being made by a robot. And that doesn't mean that they're being displaced from a job. That doesn't mean that's now a manufacturing job that's no longer available. That just means that the job has shifted away from building the object to designing the object. So for our students who may be in the inner city, for example, we're thinking about the ways that these technologies integrate into their everyday lives in the context of the city. How many objects do they use during the course of the day that they might not even think about that was manufactured by a robot? Whether it's their cell phone, or their computer, or their pencil, or their pen, or their light bulb, or their doorknob, or the car they get in, or the bus that they drive on, or even the door frame that they use to enter into the classroom. And then how can we make this thing better? How can we actually get some production going? Do we integrate our 3D printer and design the new solution that helps their locker be more effective? Or is even a product that we can market? This is something that we have to find really exciting ways to be integrated for. Or if we even think about drone technologies, that's something that is super duper important when we think about even the urban context, because we can imagine a future in the city where a lot of the logistics work that we get done by parcel delivery, or even eventually standard mail delivery may be done by drones. And can we get out in front of that? Putting the technology in the context for our students, whether they're rural or in the inner city, creating an excitement around that leads to motivation, solving problems, and then making career connections. Really, really good question there. Liz, thank you for that comment. That differentiation between robotics and AI, and taking a survey there, it's a useful one to make. Right now, when we think about artificial intelligence, we're still in this place where oftentimes it's segmented as a particular portion of computer science, and usually really highly specialized. I think that giving our communities, our stakeholders, this understanding that robotics and artificial intelligence, they work together often, but are separate things, separate experiences, methodologically, in which we work with them, and even in their outcomes, really sets expectations. It can help us understand what kind of work we want to do with them. So for our patrons that might be interested in designing language models, things like a Google Assistant or like an Amazon Alexa or even a Siri, and want to learn how to apply this different kind of technologies to specific applications. AI might be the thing that they want to do. But for those of our patrons who are looking to build and tinker and get hands-on, learn about mechanics and physics, that is the kind of work that would slot really nicely in robotics. And then we can marry those two things together to do even more complex physical work or even scientific work. That's a really exciting possibility. Some of you may be chewing on some more questions. If you are chewing on some of those questions, you can contact me directly. Desmond at nextwavestem.com. Really, really easy to get in contact. And absolutely, you can reach out about kits for your organization or whatever that you're working on. We love to have those conversations. I am Desmond at nextwavestem.com, but you can also find NextWaveSTEM on all major social media, Twitter, LinkedIn, Instagram, and Facebook, not on TikTok. I'm not experienced enough on that particular platform, but we may launch something in the future so that we can grab some engagement that way as well. But for all of our participants who have joined us today, we are so appreciative of your time. We're appreciative of your attention, and we're hopeful that you're able to take a little bit of what you learned and use that in your community with your students, and educate your teachers or your parents, just give them a sense of what can really be done with robotics. We're asking that you all stay safe. Be on the lookout for a follow-up email with a copy of the slide deck today, as well as this presentation recording. And until then, we're wishing you all very well. Bye, everybody, and we'll talk again soon.